Hey guys, welcome to question 13. So, starting off with part A, we have prove that for all integers n with n greater than or equal to 3, if 2 to the n minus 1 is prime, then n cannot be even. So, this seems a little tricky, but what we need to do is we'll prove the contrapositive of this statement. So if you guys remember the contrapositive, so if if 2 to the n minus 1 is prime, then n cannot be even. So we flip it around and we make the we negate both sides. So therefore if n is even, then 2 to the n minus 1 is not prime. So this is the contrapositive, and we're going to be proving this. So if n is even, and we know n is an integer, then we can rewrite n is equal to 2k, for some k is an element of, positive, so some element of the natural numbers. So therefore, we can rewrite 2 to the n minus, that is the wrong place, 2 to the n minus 1 is equal to 2 to the 2k minus 1. And that will just be a difference of 2 squares. So that's just going to be 2 to the k all squared minus 1, which is just 2 to the k minus 1 times 2 to the k plus 1. And here's the cool bit. So we know that since n is greater than or equal to 3, therefore k has to be greater than or equal to 2. And if k is greater than or equal to 2, then both 2 to the k minus 1 is greater than, no, not greater or equal to, no, it's definitely greater than 1. We know 2 to the k plus 1 is greater than 1. So if we have two numbers in for our number, both greater than 1, then that is definitely not a prime number, because we have two non-great positive integers greater than 1, which can times into our number, and therefore 2 to the n minus 1 is not prime. Therefore, statement true as contrapositive is true. And that will be it for part A. Next, for part B, we have the numbers a(n) for integers n greater or equal to 1 are defined as, well, this big mess down below. So these numbers satisfy the relation an plus 1 all squared is equal to 2 plus an for n greater or equal to 1. We don't have to prove this, thankfully, but use mathematical induction to prove that an equals 2 cos pi over 2 to the n plus 1 for all integers n greater or equal to 1. So induction, so we immediately start off with our first step. So with our basis, we have n equal 1. So prove true for n equals 1. Let's see, a 1 equals, 2 cos, pi, so 2 to the n plus 1, where n is 1, so that's 2 squared, which is equal to 2 cos pi over 4, which, if you guys remember, is 1 over root 2, so 2 over root 2, which equals root 2. And therefore true for n equals 1, as we have a1 equals root 2 right over here. So next we want to assume true for n equals k, some integer k, and we have n greater than equal to 1, so let's just make k part of the natural numbers. So let's see, 8k equals 2 cos pi over 2 to the k plus 1. And finally, we want to prove true for n equals k plus 1. So i.e., we want to prove a k plus 1 is equal to 2 cos pi over 2 to the k plus 2, since k plus 1 is just k plus 2. So we know the a n plus 1 squared is equal to 2 plus a n, which is just equal to 2 plus 2 cos pi over 2 to the... Let's actually rewrite it using k, since we want to actually prove for k instead. Sorry about that. K plus 1, 2 to the k plus 1. And, well, if we reuse the sort of statement as before, that's just going to be equal to 2 plus 2 times 2 cos squared pi over 2 to the k plus 2 minus 1. Oh, bit of a tight one. And this mainly comes from the same idea over here. So what we can do here now is that's just equal to 4 cos squared of pi over 2 to the k plus 2. And finally, this is all from a k plus 1 all squared. So square rooting both sides, we have a to the k plus 1 is equal to 2 cos pi over 2 to the k plus 2. And therefore, true for n equals k plus 1. Therefore, statement true by mathematical induction. Oof, bit of a tricky one over here, especially with this section. So the main idea was probably just this bit, which a lot of students kind of have trouble with. So if you remember your sort of cause identity, so we have, let's see, how should I write it? I'll write it down here. So cos 2x equals 2 cos squared x minus 1. So this is probably the sort of hard bit that a lot of students kind of struggle with. Maybe not struggle with, but probably just didn't see, because I know it is a very, very niche one. But hopefully the sort of 2's and the sort of square at the beginning probably kind of hinted at it. But yeah, very, very tricky one. No wonder it's a 4 marker. And therefore that will be it for part B. Next, for part C, we have consider the equation z to the 5 plus 1 equals 0, where z is a complex number. So part I, solve the equation z to the 5 plus 1 equals 0 by finding the fifth roots of -1. So first off, so for part CI, we can rewrite -1 as equal to e to the I pi plus 2k pi, for k is any integer. So since we're solving z to the 5 plus 1 0, so that was just z to the 5 equals -1. So z to the 5 equals, rewriting that, e to the I pi plus 2k pi. And to bring that over, z equals e to the I pi plus 2k pi all over 5. And multiple ways you can do this. So you can either have k equals 0, 1, oh, fudge, 2, 3, 4, or k equals 0, plus minus 1, plus minus 2. So for simplicity's sake, I'm just going to be going with the 0 plus minus 1 plus minus 2. So we have z equals e to the I pi over 5, e to the I 3 pi over 5. E to the I 5 pi over 5 is just e to the I pi, which is just negative 1. And e to the negative I 3 pi on 5. And finally, e to the negative pi over 5. So we can just leave it as this, and this will be our fifth roots of negative 1. So next, for part II, we have show that if z is a solution of z to the 5 plus 1 equals 0, and z does not equal negative 1, so not that, but equal these four, then u equals z plus 1 over z is a solution of u squared minus u minus 1 equals 0. Oh, bit of a weird one. So what you guys need to do first is we'll understand what z to the 5 plus 1 can be factorized into. So that can be factorized into z plus 1 times z to the 4 minus z cubed plus z squared minus z plus 1 all equals 0. And we know that since z is not equal to negative 1, that can't be 0. That means this bit has to be equal to 0. So we have z to the 4 minus z cubed plus z squared minus z plus 1 equals 0. Oof, bit of a long one. So divide all by z squared, since we want to have a z squared term somewhere. So we have z squared minus z plus 1 minus 1 over z plus 1 over z squared equals 0. Finally, we can rearrange them. So z squared plus 1 over z squared minus z plus 1 over z plus 1 equals 0. And you guys can rewrite the equation since we have z plus 1 over z squared all squared is equal to z squared plus 1 over z squared plus 2. So kind of rewriting the equation above into z plus 1 over z squared minus z plus 1 over z minus 1 is equal to 0. Finally, when we have u equals z plus 1 over z, therefore u squared minus u minus 1 equals 0. And therefore u is a solution of this equation. So finally, for part 3, or part II, hence find the exact value of cos 3 pi over 5. So first we have to solve this equation. So u squared minus u minus 1 equals 0. So u equals negative b plus minus square root b squared minus 4c over 2a. So u equals negative 1 plus or minus root 5 over 2. And we also have, since u is equal to z plus 1 over z, negative 1 plus or minus root 5 over 2. Now here's the cool trick. We know that z plus 1 over z is just its conjugate, if you guys remember. So complex number over itself is just going to be z plus its conjugate. And finally, if you add a complex number and its conjugate, the main reason is also because absolute z equals 1. So the modulus is also 1. Therefore, when you put 1 over itself, you just have the conjugate. So we have 2 times the real part of z when you add it to its conjugate, right? So finally, we have the negative parts of, not the negative parts, we have the real parts of, let's see, z equals e to the plus minus I pi over 5 and e to the plus minus I 3 pi 5. So therefore, we have u, since u is equal to that, u is equal to that. Therefore, u is equal to the real parts of these, which are 2 cos pi over 5 or 2 cos 3 pi over 5. Ooh. And finally, since we have 1 minus root 5 over 2 is negative, is a negative number, and 1 plus root 5 over 2 is positive. So we know that for cos, any angle in these two quadrants are positive. So I hope you guys remember all stations to central, or any kind of combination for that. So that means that cos pi over 5 is positive, right? But cos 3 pi over 5 is going to be in this quadrant, so somewhere here, right? Cos 3 pi over 5, which is going to be negative, right? Positive, negative, which means that cos 3 pi over 5 is therefore equal to the exact value of 1 minus root 5 over 2, I think. Oh, sorry, that was 2 cos pi over 2 is equal to 3 pi over 5 is equal to 1 minus root 5 over 2, which means that finally cos 3 pi over 5 by itself is equal to 1 minus root 5 over 4. And that will be it for part I of part C and question 13 overall.